And now we will welcome the final talk of our session, which will be a very nice addition of that shifts a little bit the gear to the computation again. And we welcome Sahar ben Rached. I apologize if I don't pronounce correctly. And she will tell us about running Qiskit on yet another device, a 2-qubit quantum processor. I'm very curious if we will have some of the security questions raised as well. So Sahar, the stage is yours.
Thank you very much, Oxana. So hi, everyone. My name is Sahar ben Rached. I'm from Tunisia, and I will be presenting my master thesis work, which is entitled Running Qiskit Algorithms on a Superconducting 2-qubit Quantum Processor Utilizing a Custom Hardware Platform. This master thesis work was developed at the Institute for Data Processing and Electronics at Karlsruhe Institute of Technology in Germany. Of course, jointly supervised with my professor, Murat Elmini from the University of Semenar. So as a general outline of this presentation, I will start with the project objectives and present the experimental setup, the steps for the project implementation, the test and validation phase, and end the presentation with the conclusion and an outlook of our work. So, a general setup of a superconducting quantum computer includes a quantum processor. So this is the chip that includes the qubits and connects them. And for our experiment, we are using specifically a Transmon-based superconducting quantum chip that was developed at NIST. This quantum processor is installed within a cryostat that would provide the near zero. Okay, start my video. Sorry for the interruption. So the quantum processor is installed within a cryostat, which would provide the near zero Kelvin temperatures, which is needed for the control and readout of the quantum states within a superconducting qubit. So in order to design algorithms, schedule operations, and read out the state of a quantum computer, we would need a control system. And for my work, I used the QiController, which is an FPGA-based system developed at the IPE, which is used for the control and readout of superconducting qubits. At a higher level, we will need the quantum framework or programming language that we will use in order to design our operations and our algorithms. And in my work, I will be using Qiskit for this purpose. And Qiskit is a quantum programming framework that's developed by IBM. And the main objective of my work is to add the QiController as an external hardware provider to Qiskit so that any quantum processor that is commanded by the QiController would enable the execution of algorithms designed using Qiskit at a higher level. So, starting by presenting our experimental setup, and this is the QiController system. This is what the board looks like. And if we take a closer look at the internal architecture or the microarchitecture of the QiController, we will see that it is heterogeneous and a multiprocessor architecture. And if we look specifically for the FPGA processor, we can see that it is at this level that we schedule the operations and generate the pulses in accordance, of course, to the operation that we would like to execute. And there will be the DAC, the digital to analog converter, which would apply the signals to the qubits. And then from the qubits, we will get the signal again, and we'll convert it using analog to digital converter and record the measurement result within a recording module. And of course, we would need a programming language at the user level, which would make it easy for users in order to command such a system. And the QiCode is the native programming language which QiController supports. So more on the QiCode. The QiCode is the high-level description language for the QiController. It's also developed at the IPE, and it is mainly advantageous to calibrate parameters of the experimental setup and allow the users to program and operate on qubits at a very, very low level. So starting from the very beginning, it's interesting to see that the QiCode uses object that we call the QiCells object, where we can store the qubit properties. This can, of course, include the frequency of the qubit and parameters such as the decoherence parameters. And using the QISL's objects, we can design experiments and we can describe them. For example, in this case, we are describing the operation of applying an X gate using the properties of the qubit to, of course, have better accuracy for the execution of our experiment and therefore minimizing the error, of course, at the time of the measurement. And in order to execute our experiment on a designed or designated processor, we use what we call the QI object, which would recreate the circuit and the gates that we would like to apply, and then run this job on a specified backend, which we will call QIC in this example, and using the sample, which is a QISL object that would take into consideration the properties of the qubit that we are using in our experiment. So more of on the IBM Qiskit framework, if you have not used it before. So the Qiskit is programming, is used for programming quantum computers. You can use it to operate at the pulse level, but also on the application modules level, such as in finance and machine learning. And Qiskit actually implements or englobes multiple elements. For example, Terra for designing circuits, IR for the simulators, Ignis for the noise and error mitigation algorithms, and Aqua for the application modules. Although I must note that this may be an outdated architecture of Qiskit because there have been many updates, especially at the level of the application modules. But most interestingly, what we will be needing for this project, which is the expandable module that allows us to integrate new hardware providers to Qiskit. We will be using mainly this module in order to add the QiController as a provider to Qiskit, and that's how we can link the QiController with Qiskit. Now for the implementation. So usually, if a user would program or design a circuit using Qiskit, they would follow a set of instructions, which starts by creating the quantum circuit, applying the quantum operations, which we will be calling quantum gates, and then call the hardware provider, specifying then the backend, running the circuit, retrieving measurement results, and then visualizing results using visualization tools or features integrated within Qiskit. The project, we had the goal of keeping the exact same architecture, or let's say the exact same set of instructions, so that any person who is accustomed to using Qiskit would not find any difficulty in running their algorithms or circuits on the QiController backend. So the goal was to keep the same environment for users and allow the opportunity to everyone to experiment with the QiController if it is added to Qiskit with no change in the structure of using Qiskit. So following the same logic, we will design, create quantum circuits using Qiskit. We will apply our quantum gates. And in order to call a hardware provider, we have created what we call the QiController provider class. This is mainly to specify which backend or which processor is now connected to the QiController, and that will be the processor we'll be using for the execution of our operations. And then for the QiController backend class, this is mainly used in order to translate the Qiskit instructions into instructions that are supported by the QiCode, which will then be directly submitted to the QiController and thereafter to the processor. It's also the class where we run the circuit on the specified processor. Now, to retrieve the measurement results, we also have created the QiController job class. And as you can see, this is mostly guided within the provider interface by Qiskit for the addition of new hardware providers. And also keeping the same structure, we'll be using the visualization tools from Qiskit in order to retrieve and have a better display of our measurement results. So focusing more on the translation and how we run circuits from Qiskit to QiCode and thereafter to QiController and the processor at a lower level. So before I start into the details of how we implemented the translation routine, I would like to go through briefly how we can command or control the state of qubits within a superconducting architecture. So this Transmon qubit is a type of superconducting qubit that is mainly manufactured using two superconducting electrodes that are connected by Josephson junction, which yields the anharmonic energy spectrum. And then it would be used, of course, to confine the computational space within the ground state and the first excited state, which will be referred to as the 0 state and the 1 state for our computations. Now, the Transmon is modeled as a two-level system, a quantum two-level system, and this is the Hamiltonian of the qubit. It's at h bar omega q over 2 sigma z, where omega q is the qubit frequency and sigma z is the Pauli Z matrix. Now, in order to control and read out the state of our qubit, we connect to a resonator, and this connection is mediated by an electrical field, and the Hamiltonian of the system is described using the Jaynes-Cummings model. So we can see that the Hamiltonian of the system, let's say it's the summation of the resonator, the qubit, and the coupling Hamiltonians or energies. Now, since this presentation is focusing more on the qubit control, I will not explain further the readout, but I will be going through the qubit control, how we can actually manipulate or operate on the state of the qubit to be in the ground state, the excited state, or the intermediate states. So in order to control the qubit state, we send and execute microwave pulses. And it is actually the parameters of the pulse that determine which operation we are applying. So the frequency of the pulse is resonant to the qubit frequency. And for the Transmon case, it's usually between 4 to 8 gigahertz. The pulse amplitude would determine the rotation speed, and the pulse phase would determine the rotation axis, and the pulse duration would determine the rotation angle. So based on this description of how we control the qubit state, we can design quantum gates for superconducting qubits. And this is what I will be explaining, starting from this slide. So first of all, the QiCode was not presenting any higher description of quantum gates up at this level. So in order to make the translation from Qiskit instructions to QiCode direct, we implemented the quantum gates on QiCode, and now we can call them QI gates. And that's how we can directly go from series of instructions written in Qiskit to an equivalent instruction sequence that's given in QiCode. So starting with the 1 qubit gates. So in order to implement the 1 qubit gates, it's important to understand that operating on the state of the qubit means or refers to the rotations around the axis of the Bloch sphere. And again, we are needing this, this implementation of gates on QiCode in order to make the translation from Qiskit circuits running directly. So based on this, we define the microwave, we define rotation around the x-axis as a microwave pulse at the qubit frequency with the 0 phase, and rotation around the y-axis as a microwave pulse at the qubit frequency with the pi-half phase, and rotation around the z-axis as implemented as a virtual z-gate. So this takes us to the definition of the x-gate as a microwave pulse at the qubit frequency with 0 phase and a rotation angle of pi. And the y-gate, the microwave, it's the execution of a microwave pulse at the qubit frequency with the pi-half phase and a rotation of angle pi. And as you can see, the only difference between the application of the x-gate and the y-gates, it's just laying in the phase of the signal. Now for the Hadamard gate, or shortly the H-gate, it is described as or defined as a rotation of pi-half around the y-axis, followed by a rotation of pi angle around the x-axis. And as you can see, the amplitude of the signal, the amplitude of the signal that defines the rotation of pi-half around the y-axis is half the amplitude of the signal that defines the pi angle around the x-axis. It's mainly because the rotation is defined by the amplitude of the signal itself. So again, we can, of course, create more gates using this. So we've got the U2 gate, which is decomposed into rotation around the z-axis, the y-axis. And as you can see, the only shift in the amplitude is showing the rotation around the y-axis. And why is that? It's mainly because we have used a virtual z-gate in order to implement the rotation around the z-gates. around the z-axis, sorry, and this is not showing as a shift in the amplitude, but rather a shift in the phase. So it cannot be observed at this level, but of course it's implemented. So as for the U3 gate, it is decomposed as a sequence of instructions or rotations around the z-axis and the x-axis. And again, we can only see the shift in the amplitude of the signal that define the rotation around the x-axis, because again, we are using virtual z gates. And this is mainly advantageous because since we are not physically implementing a signal at the implementation or the execution of z gates, and that actually decreases the error rate when we would like, of course, to have better execution of our gates and a lower rate of errors. So in addition to the 1-qubit gate, we have implemented the 2-qubit gates, which are mainly the ISWAP gate and the CNOT gate. So the ISWAP gate is implemented by driving exchange oscillations between the 2 qubits at the difference of their frequencies. And the CNOT gate is a sequence of RX, RZ, and ISWAP gates. Of course, much more details and references are actually in my master thesis report. So if you are interested in, physically speaking, how this is all implemented and how this was all designed, then of course, I would like to invite you to look more into the details of this in my master thesis. So now that we have our quantum gates, the main thing to do now is to translate a sequence that's coming in Qiskit code, translate it to a QiCode. That means it is now in terms of QI gates. Then submit the sequence to the QiController, and from the QiController, it will be submitted to the processor itself. So let's see how this goes. So if we have a quantum algorithm, which we are using Qiskit to design. So in this example, I'm taking a quantum circuit of 1 qubit, and then I'm applying a sequence of instructions or sequence of gates that is the X gate, the Hadamard gate, the Z gate, and then the Y gate. Then I would measure my qubit, and of course, I would like to use the Qiskit visualization tool of a circuit in order to see clearly the sequence. So this sequence that is given in Qiskit, at the level of the QiController backend class, it will be converted into an equivalent sequence given in QiCode. So this is what we create. We create a QI job, which is an object that is supported and specific to the QiCode. And this QI job would create a circuit having the same number of qubits, apply the exact same sequence of instructions, including the measurement, and then again, at the level of the backend class, we would run our job on a specified QIC or a QiController processor or backend, and then, of course, taking into consideration all the qubit properties that are stored in the sample object. So since now we have the sequence in QiCode, and of course, this would be directly submitted to the QiController. And from the QiController, this is the sequence of signals that we create. It is a sequence of signal that, of course, implements or incorporates the same order, and of course, implementing the gates that we have created at the level of the QI job. So this is practically how we did the translation, and this is how we went from Qiskit to creating the same sequence of instructions, and then submitting it to the processor. And of course, at this level, we can retrieve the measurement results, and that would be the end of our experiment, seeing the example that I gave. Now for the test and validation. Now, of course, if we are going to operate on a superconducting chip, there is a very big set or a very big setup to work on. And the experiments usually start by the calibration of our electronics and our measurement setup, and of course, the qubit characterization. And why qubit characterization is important? It's mainly because it includes the details that we need in order to operate on our qubits. That means the frequency of the qubit, the decoherence parameters, the pi pulse duration, and this is all important in order to define accurately, or as accurately as possible, our quantum operations, and that's how we reach, let's say, a relatively low error rate. So, as I have presented before, so the qubit will be connected to a resonator, so the resonator would inform us more of the readout state, but also it's important for the application of gates. So we define the resonator's frequency, which will help us therefore to find the qubit frequency. And then the electrical delay calibration. The electrical delay would be the time that's needed for the electrical field in order to, or the electrical pulse to reach to the qubit. This is also important to consider. And then measuring the pi pulse time. The pi pulse time is practically the time that's needed for the qubit to go from the ground state to the first excited state. And vice versa, because it's important in order to define our operations, especially the X and Y gates. In addition to the additional parameters that we can, of course, characterize are the decoherence parameters, or specifically the T1, which is the energy relaxation time. It's the time that characterizes the decay of the quantum state or the qubit state from the excited state to the ground state. And of course, we would need to operate our sequence of instruction within the window of the coherence time. Otherwise, it would be, of course, difficult in order to create operations and do correct measurements. Also for the dephasing time, T2. And as we can see, both of the parameters are at the order of the microseconds, and usually quantum gates are at the order of the nanosecond. So we practically have enough time to do operations, but still, if we are applying a long sequence of instructions, then we are at a very high risk of an error rate at the end. So also, it's important to do the state configuration. For the state configuration, we do multiple readouts or measurements of our qubit at the states of excited state or the ground state in order to create these clouds, okay? And it's according to the concentration of our measurement results, we would define which coordinates correspond to the state 1 and which coordinates would yield the state 0. And this is very important at the distinction between the states at the measurement level. Of course, this would tell us also about our measurement performance and whether our results would be correct or not. And as you can see, after creating the clouds, we distinguish between the states, of course, and this is important at the level of the measurement. Now, in order to, after the calibration and the characterization work, I'm presenting to you an example of our results. So, as I have presented before, we are keeping the exact same architecture, or let's say sequence of instruction, in order to work with Qiskit and execute on their backends, for example, IBM Quantum backends or their integrated partners. So we are following the same workflow. So first of all, we start by creating our quantum circuit using Qiskit. In this example, I'm creating a circuit of 1 qubit, and I'm applying the sequence of instruction Hadamard, Z, and Hadamard. And then I'm applying a measurement, or I'm measuring my qubit. So the next step would be to call the provider, the hardware provider, which of course is we use the QiController provider class, which specifies which backend we are using for our experiment. In this example, it's the NIST quantum chip, which we have defined at the very beginning of our experiment. And then the sample, it's the object that defines the qubit properties, which have been calibrated before this step, which is the 3 or 2 slides before. And then in the end, we would like to specify the backend. So the backend, we would create a backend or hardware backend based on the processor selected and the qubit properties. That's mostly, of course, in order this class, at this level, it's where we have implemented the translation routine, and that's where we create the QI job and execute it on the QI controller. And once we have the execution, then of course we can retrieve the results. If, of course, you have used Qiskit before, this is more or less the same logic, which is choosing the backend and then running your quantum circuit for a certain number of shots. In this example, I'm just running for 1,000 shots. And then I would get my results in terms of counts. Counts, it's the dictionary variable that would indicate which quantum states were measured and what's the frequency of measurement of the states. That would tell us directly what's the probability of measuring each state for our experiment. And then we can use the plot histogram feature from Qiskit in order to have a better display of our results. So according to the example that I gave in this circuit, if the qubit, of course, is initialized to the state 0 at the very beginning, the evolution of the state would yield to the state 1 at the very end. And this is what we get. So this is the histogram of our results for this experiment. And as you can see, the highest probability of measurement is given to the state 1. However, of course, we can see that there is still some relatively high error rate. This can be explained by a number of reasons. For example, maybe we would need to have more accurate methods to initialize the qubit. Maybe we need better calibration of our signals. Of course, this enters within the outlook of our project, but the general statement is that this measurement results says that the execution works as expected. We expected to have the state 1 at the end, and we have the highest probability or the highest frequency of measurement results given to the state 1. And with this, we validate or we verify that the operations are correctly translated from Qiskit to QiCode and correctly executed on the QiController level. So as a general conclusion and outlook, we have implemented indeed the integration between Qiskit and the QiController. This went through especially two big steps, which is first of all the implementation of quantum gates on the QiCode, and then the integration of the QiController provider to Qiskit using the provider interface. For the measurement, of course, we still have a relatively high error rate, but that's of course something that we can ameliorate with experiments and with of course, as I said, better methods of calibration and characterization. And within the outlook of our work, we will be testing on a 2-qubit chip, because at this level we did not test on a 2-qubit chip, only on 1-qubit chip. But of course, that's included within the roadmap of this project. And of course, we would like to test whether high-level quantum algorithms can be executed directly, for example, from the modules of Qiskit applications. So that was all. My master thesis is available upon request, and you can reach out to me either via LinkedIn or email. And thank you very much.
Many thanks, Sahar, for this great talk. And let's see how will be the questions. So far, we've got a couple of them. They were similar, actually, and both wanted the thesis of yours that you just announced that it can be got by request. I have actually found something on GitHub, but now I'm wondering, on GitLab, and I'm wondering if it's your thesis or not.
It is, yes. But I actually had like the feedback that it's not downloadable. I'm not sure. So you can test and let me know if it's downloadable. Otherwise, I will update the link. Okay,
so then let's see if Said and GitHub will try to download it, and then we'll come back with the feedback. We have a great thank from Handi for your amazing presentation, and Nasser Balaloui has a question. So the very first talk by Nahan was about error mitigation, and would any of the tools provided here help with your accuracy? Tools provided there in the first talk of Elham will provide the help with your accuracy.
Okay, so I should mention that 17% of error rate is quite high, for example, for error correction algorithms. So what we have concluded is that we should have better calibration of our measurement electronics and better calibrate our gates. So it's mostly, the first step would be to try to decrease that error rate using better calibration methods for our setup. And then, of course, if there is still some work to do at the level of error correction or error mitigation, then that will be on a second phase.
Okay, seems like the thesis is downloadable. Many thanks for the reply. And have you thought about implementing multi-qubit gates? Akash is asking.
Yes, we did thought about this, but we did not see that it is necessary, because with the set of gates that we have implemented, it is a universal set of gates, and you can create or recreate any other quantum operation only based on this group of gates that we have created. Otherwise, there's really like too many quantum gates to implement. And of course, that's possible, but we wanted to be efficient in terms of signal application, and of course, in terms of number of gates that we have. But it's expandable. You can even try out with QiCode and create other gates based on what we have already implemented.
Very nice. Thanks a lot from Akash as well. And the next question is, are you making the qubits experimentally or using the IBM QC experience? And does a QiController works similar to Arduino modules? The SIT is asking.
No, we are not using the IBM experience since we have created the provider interface in order for Qiskit to recognize the backend and the provider coming from the QiController. We did not use the IBM quantum experience. As for the QiController, it's not based on Arduino, but based on the FPGA. Well, it's a microcontroller, so it should have the same logic of using any other microcontroller, but of course it has its advantages.
Mm-hmm. Okay, many thanks. And I also have a short question, but it's rather about formality. So I wonder how it works, whether you, and thanks from Sid, whether you needed some kind of communication and agreement with IBA Quantum or Qiskit providers. And the other question is, can your controller be used by other people who have small quantum computers made, or is any quantum computer that wants to use Qiskit, does any have to make its own controller?
So for the first question, we do not have an agreement with Qiskit or IBM Quantum because Qiskit is an open source. It's open source, so we can add to it, or we can, of course, use it for projects. And the IBM Quantum team is aware of this project. But of course, the QiController is developed and it's used at the IPE, but it's not commercially available. So it's not available for the public. And maybe at the level of the commercialization of the backend, there will be more agreement and more talks with IBM. Yeah, so for the QiController, as I said, it's available at IPE, and for the QiCode, it's used by some research institutes in Germany. So they have access to the QiController, and therefore they have access to using the Qiskit QiController provider. Yes, I'm sorry if you could remind me of the third question.
No, I think that is mostly all. I was just wondering if every computer that wants to use Qiskit has to do this, or maybe Qiskit already has a controller that one can use for paying, or I just wonder if it's if it needs to be locally next to your computer, or if it can be some element which is located somewhere away from your own computer. This was my question.
No, you can do it once you have access to any quantum processor or a setup of a superconducting quantum computer. There is actually a guide that's called the provider interface that's available to everyone, and it's published on Qiskit documentation. Then it gives you an idea of how you can integrate new hardware providers. So this also enforces the idea that it's open source, so you can use it in order to add, of course, a new hardware providers. But in the end, it actually depends on the system that you are using. So as you have seen, there is an extensive use of the QiCode. There is an extensive use of the setup, of the experimental setup that's available at the IPE, especially at the level of testing. So if you have access to a similar setup, of course, in any company or research institutes, then there's definitely a way of integrating it to Qiskit, as we have done. And one more thing is that, as I remember, there's already two partners that you can access their hardware using IBM Qiskit, which is the IonQ and the AQT, I guess. So most importantly, it's expandable, and usually this work is done between IBM Quantum and their partner company. It usually takes, of course, less time than I took in order to implement this project, but this kind of agreement is existing already.
Many thanks, Sahar, and we are now closing this session, and I ask you, as I did for all other participants, to close it in your native language, if you don't mind.
اوكي يعيشكم، وكانت لي تجربة باهية برشا انه خدمت الاودينس معناتها كبيرة. هذه كانت أول مرة، ونشكركم برشا على حضوركم، وإن شاء الله في وإن شاء الله في experience أخرى.
Great.
Thank you.